But this is really more of an informal thing. You can ask questions. You can actually come up here, show us how you might want to do something or how you might process something. Basically, it's kind of everybody teach everybody else type thing, and basically I'll moderate it. And any kind of questions you have, any kind of questions that I have, we basically help each other out. So basically, what I'm going to talk about is there's been a good deal of debate on taking proper flats. So how many people of you do CCD imaging? Let's see a hand here. Okay. And so let me get you. You're Torsten, right? Yep. And what was your name, sir? Gary. That's right, Gary. And Richard over here. Anybody else do CCD imaging? Nobody else. Okay. Let me ask you all the question. How do you know that you're taking a good flat?
I put it on the table and see the level.
Okay. Carpenter's level?
Yeah.
But really, how do you know that you're taking a proper flat? That's the question. And there's really no easy answer. And the reason why there's no easy answer is because there's too much variability in CCD cameras nowadays. You can have different kinds of CCD cameras. They react differently. So I've heard stories that, okay, some people take it, 10 to 15,000 ADU. And then other school of thought is like, 50% of the full well. Another school of thought is, 2/3 full well. Now, who's right and who's wrong? Now, there's really no right answers, and, well, there is a right answer. And the right answer is you need to characterize your camera. You need to go and take data, and you'll get a chart like this, and believe it or not, the actual data that you take is right here. This is your data here, and this is the other data line. The rest of it is number crunching, which is actually fairly simple. This is a method called Photon transfer curve. It was done by NASA JPL when they were using the Vidicon 2s, I think they called them, back in the old days with the Voyager spacecraft, when they tested they didn't have CCD technology back then, but they had the picture tubes. And they would use this method to characterize their picture tubes. In fact, this method is still used today by NASA because it is by far the best method to characterize a CCD camera. You can think of it like interferometry for sensors. You can think of it that way. But what it does, get into how to do this because this in itself was a topic in the 2009 Winter Star. Richard Crisp actually took a lot of Jim Janicek's work, who worked at NASA JPL, and he wrote 2 books. And he took those 2 books and condensed it to the point where we could understand it. And he's got on his website and charts on how to prepare this kind of data. But what I wanted to show you, Richard Crisp, and his website is called narrowbandimaging.com. And a lot of people don't like him because he is pretty much very straightforward and not very tactful. He just pitchfork,
C-R-I-S-P?
C-R-I-S-P. Is something that looks like this, okay? And I'm going to demonstrate to you because I have, okay, this is, so I got the SC10 up here. All right, well, what you really want to do to take flats, where you want to take flats is, well, first of all, I'm going to get into, let me explain to you the 4 regions of this curve. What this tells you, this curve over here, something's a little bit off. Okay, this graph, by doing the data crunching, gives you a lot of information. First of all, you get your read noise over here. This shows you where the read noise is. Okay, this shows you where the shot noise is. And this shows you where your full well is, where it starts dipping down. And this is your fixed pattern noise this data, you can find where, what your read noise is. Like in this case, it's 11.2 electrons. You can find your gain down here. You can find your dark signal non-uniformity, which is the way they test sensors at, for example, at Kodak. You have your fixed pattern noise. Now, here's the thing. With flats, what you're trying to do is you're trying to get rid of fixed pattern noise. Fixed pattern noise is your dust donuts. You might think of it that way. But it's also the checkerboard effect that you get on the sensor. Okay, now the problem is that look where this is. This is way out over here, and your shot noise is actually higher than your fixed pattern noise. But you still get fixed pattern noise, and this is what you want to get rid of. So where do you take your flats? Well, this is where you take your flats. You want to take your flats before you get to the point where any one single pixel saturates. What does that mean? As high as possible. 3/4 to nearly full well. Okay, and now here's the interesting thing. This is an ST10. My ST10, this is my ST10. It saturates at 41,000 ADU. Not 65,000, but 41,000. So this is why you hear so many different schools of thought because, oh, well, it works because this, or I can't go past this because it saturates, you know, and so you have this such a varying school of thought out there. But the reality is, what you want to do is you want to be about 2/3 to 3/4 of this full well of 41,000. So that would be right in this range right here. So, but the thing is, you need to know what your camera's doing. And you have to do this kind of data reduction to know what your camera's doing so that you get flats that are correct. Okay, now any of you are using an ST10, especially from SBIC, you want to make sure where your full well is. And that's actually very easy to do without really going through all this data reduction. I do this because I'm an engineer and I can do this kind of stuff. I like doing this kind of stuff. Basically, what
What's
you
a
do.
simple way to find your saturation?
Well, that's what I'm going to show you now. Unfortunately, I don't have Maxim DL in here because I don't have the DVI. So that's what I was going to show you how you measure it. But basically, if you open up the information window and you pick an area on your sensor in the middle, okay, and you read it, you're going to get average, maximum, minimum, standard deviation. So what you want to look at is your average, okay, and your standard deviation, and your maximum pixel. So what you want to do is you want to look at the whole sensor area and make sure that, number one, you're not going above 65,000. Any one pixel going over 65,000. Look at your average and look at your standard deviation. Now, the average and standard deviation, this is basically taking flats. This data reduction is you take a bunch of flats with varying time so that you get very low levels to the point where you saturate within a 60-second time frame. So this is actually very fast to do. You could do it in 1 hour. Okay. And basically what happens is there's a correlation. So from the low level, like for 1 second exposure on the flat box, I got 16, 54, and 36 over here. This is standard deviation. Okay, so you got that information. Yes, Doris?
Per exposure time, do you take like the average of a bunch of flats or just a single?
No,
flat?
this is a single flats for this type of data reduction. Then you can do another curve called the flat field transfer curve, which I wanted to do. I didn't have time to do it, but I would have liked to do it. And basically what that shows is that as you increase the number of flats, you go from a region, what you want to do is, this is the controlling region, shot noise. That's statistical nature of light. The noise, the square root of the signal is your shot noise, basically. And so what happens is, you want to, there's a point where this crosses. So when you add up all your images, this actually gets on top. So what you want to do is you want to bend this fixed pattern noise so it matches your shot noise. So it takes a certain number of electrons collected in your flats in order to move that fixed pattern noise so that it is at a slope of 1/2 on a log curve versus a slope of 1 over here. So basically what that entails is you need to collect the research has been done, you need to collect 500,000 electrons on all your flats. So in the case with the ST10, I have 41,000 electrons, or 58,000 electrons at full. So you take 3/4 of that is, say, about 30,000. So I would, with this camera, I would take my flats at 30,000 ADU. Okay, and then basically 30,000 or 30,000 ADU times my my gain, which I measured over here, or is it right there, 1.41 electrons per ADU. Multiply that, I would have. No, that would give me, no, that won't give me 500,000. That would just give me, for a single image, give me, you know, roughly what, 30 times, say about 45,000 electrons. So now I have 45,000 electrons. So now I gotta take, if I take 500,000 divided by 45,000, that tells me how many images I need to collect, how many flats I need to move this fixed pattern noise to match my shot noise. So that way you're not adding noise into the image, unless you do a correct number. Now I'll give you an example. I have it a 16803. I've worked out the math. Basically it comes out to 9 images to get a 500,000 electrons. I have an ST80, a FLI 8300 camera. Well, that takes 28 images, 28 flats per filter to get 500,000 electrons. So that's a big difference between the two cameras because of the well depth. The 16803 has a well depth of 100,000, while the 8300 sensor has 1/4 of that at 25,000. Okay. So another nice thing about some of these charts, what you can do is you can actually look at how linear is your camera. You can actually measure camera linearity. So you can actually, you have all the tools necessary to really characterize and keep manufacturers honest. That's the big thing. You want to keep the manufacturers honest, you have the tools to do it right in your hands. So,
Is there a lot of variability between a specific model of camera?
well, I'm going to show you that's why I was showing you this with the ST10. I didn't realize I actually brought that up first, as it was really more of a test. But yes, you see that the ST10, it is saturating at 41,000.
Yeah.
Okay, which is a bit low, and it tells me that the camera is not very well tuned from SPIC, because it should be saturating at a little bit higher level. It should be saturating around 50, 55,000, not at 41,000. So they got the gain set too high. And they might have it, there are trade-offs. I'm not saying that it's SPIC's fault. There are trade-offs because sometimes when you bin pixels, okay, this comes into effect. This setting will come into effect. I never really use binning, so the 3200 is capable of binning because the readout register is double the size of the pixel, actually more than double the size of the pixel, so it can handle binning of 2x2. Professional grade CCD cameras handle several binning because what happens on the cheaper full frame cameras, when the data is read out by a horizontal register, the data gets shifted down. But if you're binning 3x3, for example, the horizontal register that they have, their bucket isn't big enough to hold the data, and it overflows. Okay, so the important thing is that they may have chose this level for a particular reason, but I don't like it. I've actually told Matt Longmire that from SPIC. So I actually sent him this data and I showed it to him. I said, "Oh, this is what's going on with your camera." Actually, there was an issue with one of my friend's camera, and actually it was in here. Not really much of an issue though. Actually, the ST8300 is really a good camera, good bang for the buck. This is okay. I was going to show you the other one. Can I stretch this over?
Yeah, grab it at the bottom.
There it is. There's the ST10. Well, I don't have his. This is my guide camera here, so I'll show you what my guide camera looks like. Forgive me, I'm a little new to a Mac.
It'll come in time.
Alright, how do I make it bigger? Where's the thing at? Usually down here there's a little zoom
It's
thing.
up at the top.
Okay, well there's a slide. I'm used to the slider. Is that getting better?
There may be a slider.
Yeah, wait a minute.
Okay. For example, this is my guide camera, you know. Can I close this?
Sure.
I don't know what that does, but this is my guide camera. My guide camera, you'll see that it saturates at 57,000. Okay. The read noise is 4.22 electrons, which is 1.22 electrons higher than the manufacturer's stated specs. So it basically throws it about 40% over their specs. It has the read noise or the gain down here, my fixed pattern noise, and again my full well region right here. So when it starts curving down, that's your full well. But you know, going back to Bob, right?
Oh,
Your original question is, how do you know the easy way? How would you figure out?
I can
Where
see
you're
it,
at.
I can see it now, it flattens out.
Right.
Yeah.
So basically what you do is, look, if you look at the numbers,
Yeah.
the numbers start increasing, your standard deviation starts increasing up to a point where it starts to decrease.
Yeah.
And the decrease is very sudden. And that means you reach the full well. So you go, your standard deviation, I can't read it up there, it looks like 591.3. And then all of a sudden it drops to, yeah, 591.3. Then all of a sudden it drops to 0. That's a very sudden drop over there. So you know that this basically, I would take this data, well this is the averages too. So 62,978 is basically your full well. Okay, so you want to take 2/3 or 3/4 of that, which brings you about 42,000, and you want to do your flats at that level right here. Okay, now then you have to look at how many electrons you have and see how many images you're going to need. Like I said, on some of these cameras with 25,000 full well, 25,000 electrons full well, you need 30 images. When you get to 100,000 full well, you only need 10 images. And if you have, for example, some of these professional cameras or professional sensors which have like 200,000, 300,000 full well capacity, well, they only need 3 or 4 flats. And because they get to 500,000 real fast. So it's okay. And like I said, Richard Chris has done a lot of great data reduction and has spreadsheets on his website that shows you how to create this kind of graph if you want to get into that. But like I said, the easy way is to follow these numbers, see where it starts dropping off, and where it drops off, you kind of iterate around that to find exactly where it starts to drop off. You get your maximum pixel value. Okay, make sure that no one pixel is over 65,000, because that will also drop you off. Okay, so if you have some hot pixels that are getting to 65,000, maybe you can ignore them if it's just a couple. You can use a hot pixel kernel and MaxMDL to remove that. I wish I had my laptop so I could show you some of those things, but or pixel maps to remove defects on your sensor. But the main purpose of this is you can't go by what people say where you should be taking your flats. Okay, there's no right answer, there's no wrong answer, but what I'm saying is the right approach is to actually go into your camera, measure this data, okay, find out where your maximum pixel value, where your full well is. Like I said, again, full well is where these numbers suddenly drop off at the top, okay, and you take 2/3 or 3/4 of that, and that area is where you should be concentrating taking your flats. So, anybody have any questions? I'd be more than happy to answer them.
Again, how come this 500,000 number to be?
It goes into the math behind it, and I didn't bring that information with me. But if you go into the math behind flat field theory, basically what happens is, again, it goes back into this, okay? Your dust donuts is a fixed pattern noise, okay? This is your fixed pattern noise right here, and at some point it's going to cross, and you're summing up or you're averaging a bunch of images, okay? So at some point out here, these two lines cross, and the dominant noise is fixed pattern noise, which is the checkerboard effect of the sensor, imperfections of your sensor, dust donuts on your filters and on your lens. Okay, so what you want to do is you want to take this line and force it to be equivalent to your shot noise, which is light. Light is, the nature of light is shot noise, square root of the signal. And what you're doing is you're moving this line by taking multiple flats and bringing it parallel to this line, so that out here where they cross, they're in the same plane. So you're not at your fixed pattern noise is never greater than your shot noise. Basically, it takes 500,000 to 1 million electrons to get to that point where this line gets shifted to be a slope of exactly 1/2. Fixed pattern noise is always a slope of 1 on a log-log curve, while shot noise is always a slope of 1/2 on a log-log curve. So if you have errors in your data, you can easily see this, and I could actually demonstrate that. If I had an error in my data, for example, if the shot noise was, or the read noise was wrong, there's a formula shown on here. Let's see, if I put 23 electrons, didn't change them all. Okay, if I put the wrong data in, it's going to show up instantly. It's going to show me that too. Okay, well it's not, now it's not plotting. Let me go the other way on the numbers. This is a big error. Okay, what it's showing is that my data is no longer following the slope 1/2 line. It's coming off that line. So it's telling me that I have an error in my read noise, so, or in my offset. So by the way this wags its tail along this line, you can dial in exactly the read noise. That's why it was as precise as it was, 21.7 ADU. 21.75. So that's what it took to really get that to follow that slope 1/2 line. See how nicely these triangles fall on that line. Fixed pattern noise is a little bit out there because these were dark transfer curves, so it's a little bit of variability in that. Okay, anybody else? So remember, I'm the icebreaker. Anything you got, anybody wants to discuss is open. So any questions? If you have something that's not related, like I said, I only wanted to show about taking flats because there's too much variability and misconception out there on how to take flats, or where they should be taking their flats.
If you didn't want to go through this whole analysis, couldn't you just look at your 58, 60, 62 versus time, see where the curve changes, do 3/4 of that, and then say,
Well, no,
I'm going to do 20 flats
No,
and
but
have enough?
No.
No.
Again, you need to look at, okay, where does your maximum pixel value occur?
Yeah.
Where does the standard deviation of that? Remember, this is the average. You're reading, these are averages
Yeah.
out of the information window from Maxim.
Mm-hmm.
So out of that average, you're going to look at the standard deviation and the average and the maximum pixel value and see which is going to control. Okay, as soon as the standard deviation starts dropping off, which is almost instantaneously,
Mm-hmm.
it's very, this is very, very sensitive to full well.
Mm-hmm.
It shows you when it's happening, because as your pixels start to saturate, they all become 65,000 and the standard deviation starts dropping. It's just basic math, right? And you're
Yeah, all I was getting at is you can see where it's going to saturate
and then you basically take 2/3 of that and you should be
without even looking at the standard deviation. You can see where it's going to saturate.
Well, you should look at the standard
Oh,
deviation.
should
You should look at both. You should look at three things. Again, you should be looking at your max pixel value.
Yeah.
Because you might have a few pixels that are going to
That are
go over that.
Okay.
Okay, so you want to look at that. You want to look at your average, see where your average is, and you want to look at this standard deviation and make sure you're not dropping off suddenly. Because when you're dropping off suddenly, you're definitely reached your full well.
So,
So you want to drop it back down and then take one of those lower ranges and basically take 2/3 to 3/4 of it. If, for example, if your pixels, in my case, if the pixels are going to saturate first, a few pixels, I might actually go a little bit higher, take 3/4 and ignore those few pixels because I can remove them with a pixel map in Maxim.
So I better break down and get Maxim finally.
Yeah, actually Maxim is a very good program. I've been using it for years. I know that Richard uses CCD soft, right?
And nebulosity,
Nebulosity.
to be honest.
Right. But you can do the same in both programs.
In nebulosity too?
Hmm?
Nebulosity will do this for you too?
No.
No, I know.
Yeah. And just to give you,
You could do it, it's a lot more laborsome to try to get it out of nebulosity.
yeah. And to give you a little more information on the photon transfer curve, you can do stuff like this. You know, you measure your gain, your full well, your read noise, your dynamic range, your photo response non-uniformity, and the effective number of bits. I mean, you can do, you can get a lot of information just by doing that curve. And actually, when you do that curve, once you get experience doing this, I've done multiple of these, you kind of see things with the numbers itself. Just by looking at these numbers, you can tell what's going on and not actually have to look at the graph. That takes a little bit of experience to get to that point.
Tim,
Yes, sir.
did Maxim spit out this spreadsheet and data for you?
No.
Or you had to, you really
I
had to put all
had
this
to create.
together?
I had to create this. Basically, the only data that you're getting out of Maxim is the average and the standard deviation. That's all you need. And if you can, if your camera supports it, the offset. Okay. And the problem is most cameras don't support it. FLI and it does support a camera offset or bad. Your offset region, you can actually read out pixels that are not there. Okay, and it makes it easier because then you know, you have to put in the offset, so this is the other number that you put in. So those are the three pieces of data that you really need.
Have you ever tried to measure the shutter effects on flat fields?
Shutter,
I mean the shorter possible time that you need for taking a flat without having a shutter.
If you do a flat field photon transfer curve, you can actually measure that. You would be able to measure that. And actually, I wanted to do it, I just didn't have time to do it.
Because it varies along the frame.
Yeah. Basically, with the iris shutters, you need at least, I like to try to keep my flats 5 seconds or longer.
Yeah.
Because else you get the shutter effect.
It's just to know because
Yeah.
sometimes.
Actually, I've gotten away with the 8300, which is because the sensor is smaller, I can use 4 seconds.
Less.
Okay, 4 seconds or even 3 seconds less because the sensor's smaller sensor. But my 16803 is a bigger sensor. Well, I need to do at least 5 seconds, or else you get the shutter vane effects in your flats, and then your flats don't work very well. But then there's a wonderful program by I can't think of his name now in Spain. PixInsight is the name.
Inside, yeah.
And that's just a wonderful program for taking care of non-uniform backgrounds and things like that. It's great for that. It's a very powerful program. So, okay.
You want to tell us how you take your flats?
I prefer to do sky flats if I can. but here in South Florida, you know, out in the Everglades, because I live in South Florida, we get clouds in the daytime, so a lot of times I use a flat box, one of those Alnitak flat thingies, the electroluminescence panels. Otherwise, when it's clear, I will use the sky. I'll set up a program I use is ACP, and it automatically does sky flats for me. I just turn it on, walk away, and it does it automated. Now I won't do all 30 of them on my 8300 because takes a long time, because the sky is gradually getting dimmer and it has to compensate with longer exposures. So there comes a point in time where it says, you know what, I can't do no more, stop, and then it starts running my script for taking images. And then it'll start up again in the morning for dawn.